Hi, everyone. Welcome back. Congratulations. You've made it to the last Friday of lecture videos if you're watching them kind of in the order of one video a day, Monday through Friday. We only have two more lectures after this, which I'm sure is pretty exciting for you guys that you're almost done. So this is section 5.2, the definite integral. So I mentioned that we had something called an indefinite integral and a definite integral. And we talked about indefinite integrals in section 4.10 and how to find them. And I mentioned in the last lecture that integration itself is actually the act of computing the area under a curve. Now, given an indefinite integral where you don't know the bounds, you don't know that you're doing like looking from here to here, you can't theoretically find the area under a curve unless the area is finite, right? Um, but using a definite integral where we do have bounds like the last lecture where we were looking at, say, from 1 to 3 using a certain number of subrectangles or subintervals, we are able to compute the interval or the integral. So today we're going to be talking about how to find areas under curves using definite integrals. And I also hinted at the fact that we could be using antiderivatives to do this. That is not going to be discussed today. That will be tomorrow's lecture, or the one after this one, whenever you watch that. So today we're going to talk about how to compute areas when those areas are shapes that we know. And then the next lecture is going to be how to compute those areas when we don't necessarily know the areas, maybe when the graph's a funky looking graph. We will have just a general way to compute it using the antiderivatives that we learned in section 4.10. All right. So today again should be a little bit easier, as long as you remember your formulas from geometry. So maybe it won't be so easy. But they're all shapes that are pretty typical shapes. I'm not going to ask you for like a dodecahedron or anything like that. All right, so first, let's get a formal definition of what it means to be a definite integral. So again, we already talked about what it meant to be an indefinite integral. That meant that if you took the integral of f of x dx, you got capital F, which was the integral, plus c, where c was some unknown constant. Now, we do have a definite integral, which means that we don't have to use plus c. So now we have the integral, and you notice that we have this a and b here. So this is what are called the bounds, and they come from the bounds a to b. This is the interval from a to b, which turned into the bounds on our integral. So the lower bound always goes on the bottom, and the upper bound always goes on the top. This has to be true. You can never integrate with a higher number on the bottom and a lower number on top. That just wouldn't necessarily make any sense. So the integral from a to b of f of x dx is how it's read. And this, in terms of a Riemann sum, is the limit as n approaches infinity of the sum from I equals 1 to n of infinitely many rectangles with some width that is the change in x. So this right here is the idea of what it means to be a definite integral. Okay, we are going to discuss again how to compute definite integrals using antiderivatives in the next lecture, and that will definitely be a little bit more straightforward, but this is the more formal definition of a definite integral. Okay, if we have this function that we can in fact find the actual area of, we can say that it's integrable on a to b, or that it's an integrable function. Now, I want to note that the function is not required to be continuous and non-negative. So we did have some requirements that had a continuous and non-negative function when we were talking about some things earlier in the course, but this function can be anything at all. Um, so A and B are something called the limits of integration. All right. Recall that f of x is called the integrand and dx is the variable of integration. So x can be anything. Maybe this function is in terms of y and you would have dy. Okay, so this is a little reminder. This is the indefinite integral. This is the definite integral. And this is what they look like side by side. All right. So this is why they differ. So the indefinite integral is going to be some sort of a function. A definite integral is going to be a number because you're actually going to have bounds that are numbers. And in tomorrow's lecture, we will find a way to use antiderivatives and to actually plug those values in. Today, we are, like I said, going to use shapes and areas that we know to compute that number, and it will in fact be a number. All right, here's just a quick theorem. It says if f of x is continuous on a to b, then it's integrable on a to b. So that means if it's continuous, you can find the area under the curve, which again seems to make sense, right? Functions that are not continuous may still be integrable depending on the nature of the discontinuities. So, like for example, maybe the absolute value of x, you know that it does in fact have an area under the curve, but like it's not at the point where it turns, it's not differentiable, so you can't integrate the specific point. Um, but there is still an area, a general area under the curve. All right. Now, what we can't do is integrate over a jump discontinuity unless we look at a separate integral for each part of the piecewise function. Um, I don't know if we'll necessarily cover that in this class, but you may cover that in Calc too. I'm not entirely sure if you will. All right, so let's go ahead and do a little refresher using Riemann sums to use right endpoint approximation and calculate this integral. All right, so this is the formal way of asking for the area under the curve x squared using the bounds 0 and 2. So we can write that. So bounds 0 to 2, use right endpoint approximation to generate the Riemann sum. Now you notice it doesn't specify how many subintervals that we want to do. So I'm just going to give us some. So maybe let's just say n equals 2. We've done quite a few with 4. Let's do 2. All right, if we say n equals 2 and 0 to 2, now of course you can use n, but then it would be a very long process, and that's just something that we don't have to get into in Calc 1. Let's compute the right endpoint approximation. So first of all, using n equals 2, we know that the change in x is equal to b minus a over n. Here's our a and b, so that's 2 minus 0 over 2, which means that the change in x is equal to 1. That's a pretty nice number to deal with. All right, now what we can do is we can create our points. We can find the points. So this right here is our function f of x, right? So this was always like the integral of f of x dx. Well, now we have an x squared instead. So that tells us that x squared is our f of x function, which means that we can find the points using a width of 1 and our f of x function. So we'll start at 0. F of 0 is going to be 0. F of 1 is going to be 1, and f of 2 is going to be 4, just by plugging in those values into x squared. Now that we have that, we can use right endpoint approximation to generate the Riemann sum. So the Riemann sum is just the area under the curve. It's the sum. So the right endpoint with 2 rectangles is equal to the change in x, which is going to be 1 times f at, since it's a right endpoint, we're going to start with 2 plus, and we only want 2 rectangles, so we only add 1 more, which is f of 1. And again, we omit the left endpoint, which would be the f of 0. So this is, well, 1 times anything is just that thing, so I'm going to drop the 1. F of 2 is going to be 4, plus f of 1 is going to be 1, and so this area is going to be 5 under the curve. So what this tells us is that the integral from 0 to 2 of x squared dx is equal to 5. All right. Let's see another example. Use the formula for the area of a trapezoid to evaluate the integral from 2 to 4 of 2x plus 3 dx. So first of all, again, maybe I want to create some points. I suggest drawing all of these. It would be a lot easier to be able to visualize what's going on if we actually have a drawing. But we need points in order to actually have a drawing. So for this, I would probably choose integers to plug in. I'm not going to use half values. This is just a line, so we don't need to do that. So I will have some axes here. I know I go from 2 to 4, so I can have 1, 2, 3, 4. 1, 2, 3, 4. And I don't yet know what my y values are going to be, so I'm going to leave that blank. I start at 2 and end at 4. So maybe I'll look at f of 2, f of 3, and f of 4. And I just plug it right in here, and this is my f of x. So that's saying f of x is 2x plus 3. So if I plug in 2, 2 times 2 is 4, plus 3 is 7. If I plug in 3, 2 times 3 is 6, plus 3 is 9. And if I plug in 4, 2 times 4 is 8, plus 3 is going to be 11. So those are the y values I'm going to want to get. So maybe I'll go 2, 4, 6, 8, 10, 12. So this is 12, 10, 8, 6, and I don't need to go any lower because that's what we have here. Since I'm looking from 2 to 4, I'm not going to plot 1. I'm just going to plot from 2 to 4. So 2 is at 7, so that's like right here. Let me use a different color maybe. Right here. 3 is going to be at 9, so that's like right here. 4 is at 11, so that's about here. All right. This is the line, and we're looking to approximate the area under the curve. And when we say that, I don't think I mentioned that. We're looking to approximate it under the curve only up to the x-axis. So we're never looking to go below the x-axis. So that's why when we were doing like the rectangles, we stopped at the x-axis. I probably should have mentioned that. So for example, here we'll drop our left bound to the x-axis and we'll drop the right bound to the x-axis. And the area we're looking to approximate is this area right here. We want to know this. And this is why we want to draw it, because maybe they didn't tell you that it was a trapezoid. Maybe they just said find this using the area of some shape. Well, if we look at this, we can recognize that this is a trapezoid, though maybe it looks like a trapezoid on its side, because typically when we see a trapezoid, you see like the two bases that are the different sides, one on the bottom, one on the top. This is a flipped trapezoid on its side. So what we have to recall is the area of a trapezoid formula. So area is 1/2 base 1 plus base 2, or however you may have seen this, times the height. So the height is the constant one where it doesn't matter. One side is the same as the other side. So here the height is always going to be your width of your trapezoid, because the distance from 2 to 4 here is the same as here. So the height from 2 to 4 is just going to be 4 minus 2, which is going to be 2. So your height is 2. Base 1 and base 2 are just going to be the heights of each end side of your trapezoid. So the height for the left part is just going to be f of 2, which is 7. It doesn't matter which one you assign base 1 and base 2 to. So I don't know. I put that at base 2 just to stir things up. And gotta have a little bit of fun, right? Base 1, we can say, is maybe the other one. So that'll be f at 4, which we said was 11. Therefore, the area is 1/2 7 plus 11 times 2, which is 1/2 of 18 times 2, but then 1/2 times 2 goes away, and your answer is just 18. So that means that the integral from 2 to 4 of 2x plus 3 dx equals 18. And once we get to definite integrals, using antiderivatives in the next section, we can confirm using our power rule for integrals, and then the rule that we'll have when it comes to the bounds that we have, that we can confirm that this is in fact going to be 18. Okay. So when we're looking to evaluate definite integrals, like I said, we do have two ways of doing it. We typically don't want to use Riemann sums if we don't have to, just because it is kind of a pain in the butt. So we will use geometric formulas to calculate the area for this section instead. It will be a completely accurate area. So for example, Riemann sums, we said it was an approximation, right? So it was not going to be the exact area. Whereas when we're using geometric formulas to calculate the area in this section, it will be an exact area. Okay. Now we also have to talk about this idea of net area versus total area. So when we were looking at maybe other aspects of the course, we really only cared about like positive things. But here, when we're looking at area, positive and negative area do sometimes mean different things. And so what I mean by that is if we're looking at net area, so this is net signed area. Sometimes you can just see it called net area. It's the same exact thing. I refer to it as net area. Net signed area just is the same. So if you're looking for the net area of a function that dips below the x-axis, because so far we've only computed things that happen above the x-axis, therefore it's always positive and we don't have to worry about anything. But if now you're looking for this area of some function, and obviously we can't use any geometric formulas to determine the area of a1 or a2 here. But if we know that the area here is a1 and the area 2 is a2, well, we can compute the area, the net area. So The definition of net area is taking the positive area and subtracting the negative area. So the integral here from 0 to 2, but the net area is A1 minus A2. The quantity A1 minus A2 is the net area. The more formal definition of this is net area. It's going to be the area. It really helps if I could spell. My God. The most ironic thing is my fiance is an English teacher. I don't do well with spelling sometimes, but that's okay. So the net area's definition is area above the x-axis minus the area below the x-axis. And that'll be like the positive area below the x-axis. Obviously, you're not going to subtract a negative. And you can, in this instance, get a negative area. So you may get negative area. And so the reason why we maybe haven't talked about something like this in the past is because we maybe talked about distance when it came to derivatives. And we can never have a negative distance. That's when I said, like, what are we doing? Getting sucked into like a vacuum or like a black hole or something? I don't know, science, I don't know. But here we can have a negative area. And negative area just indicates that we're underneath of our x-axis. That doesn't indicate that we're getting sucked into a black hole. That indicates that we're under the x-axis. So I do want to make a distinction there. All right, so if we're talking about net area, where we take the area above the x-axis and actually subtract the area below the x-axis, then we have to talk about the alternative, where maybe we consider both of these areas to be positive and we want to know the total area of everything. So that's going to be the next definition. Let's do an example first. That'll be the definition after this, I suppose. All right, so let's find the net area of 2x over negative 3 to 3. All right. Let's see here. Do I have all right, let's just do it. So if we're looking for net area, obviously we need to know the area above the x-axis and then the area below the x-axis. And we have to compute those two things separately. So if we call this A1 and this A2, we can go ahead and compute the areas. Now, what I want to note is if you compute this area and you get a negative number, you do want to subtract a positive number. So for A2, you're going to consider the absolute value. So you could do like here A1 minus the absolute value of A2, because if A2 is negative and you subtract a negative, you get positive, but that's actually finding the total area. So it depends on how you want to kind of construct your equation. What I might suggest is use all positive numbers here. So even though your X and your Y values are negative, maybe just consider that they're positive and compute the actual area as if it was positive, and then you can just subtract it as normal. That's totally up to you which one would kind of make more sense though. So let's do A1 first. So the area of a triangle, A of a triangle, is obviously going to be 1/2 base times height. So the area of A1, that's funky looking, that makes me uncomfortable, equals 1/2 base, which is going to be 3, times height, which is going to be 6. So 3 times 6. So that gives us 3 times 6 is going to be 18 divided by 2 is 9. 9. So the area of A1 is 9. What about the area of A2? Well, let's consider this to be positive. So this is 1/2. Now the base is 3 because here we're considering distance. So distance is going to be positive. We're not going to be considering where it lies on the x-axis. So the distance of the base is going to be 3. The distance of the height is going to be, looks like 6. I'll go with 6. So I'll choose 6. So once again, 3 times 6 is 18, divided by 2 is 9. So net area is going to be A1, which is 9, minus A2, which is 9, which actually tells us that the net area is 0, 0, 0, 0, which tells us that if you were to combine these two areas, they're in fact the same area, and it just totals out to be nothing at all. What about if you consider the idea of total area? Well, total area is taking the negative area, but saying, well, there's no such thing as negative area, maybe. Let's consider that to be positive. We want to take the first area of the positive and the area of the negative, consider it to be positive, and we want to add those things together. So this is the difference between those two things, right? So net area is the integral from A to B is A1 minus A2 right here. But total area says the integral of the positive values is going to be A1 plus A2. So what I would want you to do is if you have a negative area, you're going to compute that area, compute it positively, and then add your two areas together to get the total area that you can possibly have. All right, so let's do an example of that. As you can see, these areas are not going to be equal. So even if we were trying to find, say, the net area here, as we will, if you're trying to find the net area, they are not going to net to be 0. Your net will be something else. All right, so find the total area and the net area of these two triangles. So again, we know the area of a triangle is 1/2 base times height. So let's first find the area of A1. Area of A1, I don't know why this makes me so uncomfortable. Does this make you uncomfortable? I'm talking to a computer screen, so I'm sure it doesn't make the computer uncomfortable. The area of A1 is going to be 1/2 base times height. So the base here is the distance from 2 to 6, so that's 4, times the height, which is the y value, which is going to be 4. 4 times 4 is 16, divided by 2 is 8. The area of A2, again, let's just consider the positive, is 1/2. The base of this is 0 to 2, which is just 2. The height of this, well, they probably should have specified, but this looks like it's halfway between 0 and -4, so we'll call that -2. But since we're considering this to be a distance, it's going to be positive. 2 times 2 is 4, divided by 2 is 2. All right, so for the net area, we take the upper area, the area above the x-axis, which is 8, and we subtract the area below the x-axis, which is 2, and we get 6. So this is why we could wind up with a negative. If the area above the x-axis is smaller than the area below the x-axis, we'll get a negative value. Now for total area, we add the two values. So we'll take the area of A1 and the area of A2, and we do 8 plus 2, and we get that the area is 10. All right, now we can talk a little bit more about the properties of a definite integral. So we talked about the properties of, say, sums, and we've talked about the properties of derivatives, and all of those properties work very similarly. But now, oh my goodness, sorry, I just stepped on my cat that is apparently lying directly underneath my desk. That's sorry. The definite integral has a different property than anything else that you'll find. So this is very important to note. First of all, the area from a to a of some function is 0, which would make sense because if we have some function and you have some point a, and you take this point and I go nowhere. Well, what's the area of a point? The area of a point is nothing. It's a point. Therefore, the integral from a place to itself is 0. For the second one, if you have the integral from b to a of f of x dx, say you want to switch your bound. So this is something that I mentioned before. Say your larger bound is on the bottom and your smaller bound is on the top. We can never, ever integrate that. We need to have the smaller bound on the bottom and the higher bound on the top. Well, we have a way of doing that. If you want to reverse your bounds, all you have to do is negate your entire integral and you can flip your bounds. So this one is very important to remember. If the limits are reversed, place a negative sign in front of your integral and then you can switch your bounds. So for example, if you have the integral from 10 to 6 of f of x dx, you can write this as the negative integral of 6 to 10 of f of x dx. And then this would be something you can actually compute because you have the lower bound on the bottom and the upper bound on the top. Because this would be the same thing as saying from 10 to 6. But 10, you always read from left to right. If you go right, you can't get the 6. So that just makes no sense logistically. All right, here's a few more properties. These are very similar to everything else we've done. So this is the same as derivatives and sums and pretty much anything. If you have the integral from a to b and you have a sum or a difference, you can almost like distribute your integral. So this is what I mentioned when we were talking about indefinite integrals. Same exact rule, but now you have bounds. So you can take the definite integral of each thing separately. The only thing that you cannot do is distribute the integral over multiplication or division. So my example last time was like, say we have the integral from a to b of x ln x dx. We cannot say that this is equal to the integral from a to b of x dx times the integral from a to b of ln x dx. This is not true. We would have to use a different technique that we don't learn in this class. but you can with addition and subtraction. All right, we also have this rule that we've used for indefinite integrals, and it holds for definite integrals as well. If you have a constant inside or attached to your function, you can pull it outside of that integral. As long as the constant, if you have like multiple things being added together, would be attached to everything. Or if it's just a single thing, you can just pull it out. And then this last one is similar to when we were talking about summations. And again, you notice that these summations on integrals are very close because they accomplish almost the same task, which is what I mentioned. The infinite sum is the integral. So if you have the integral from a to b of f of x dx, but maybe it doesn't make so much sense to do it from a to b. Maybe you have some positive and some negative and you want to split that up. You can introduce a new c where if a is less than or equal, well, not equal to, that would just be 0. So let's just say less than. If a is less than b, and you want to split this up, then if you introduce a c, you can say a is less than c, which is less than b, and then say, okay, the integral from a to c of f of x dx plus c to b f of x dx is a to b. And so the trick here is that if you have a bound on the top that is the same as the bound on the bottom, and you have the same integrand, you can actually combine these two integrals and just keep the two bounds that are different. So that's kind of the trick for this one. This is also a pretty important rule to note. And this is also important. So say if you have the integral from c to a f of x dx plus the integral from c to b f of x dx, and they ask you to write it as a single integral, what you would want to do is use the rule from before. Let's see, this one that says you can reverse your bounds if you negate your integral. And we can rewrite this by flipping this bound because we know that a is less than b, and that has to be on the bottom. You can say negative integral from a to b of f of x dx plus the integral from c, oh, I shouldn't have said b, it was a to c. I don't know, you can't change the bound, you can only flip them. A to c plus c to b f of x dx. And then you'd be able to combine these if you had specific values. Like if you were given values for these, you can actually plug values in. All right, so this is what I'm talking about. This is why I gave that example. If you have the integral from 0 to 8 of f of x dx is 10, and the integral from 0 to 5 f of x dx is 5, we want to find the integral from 5 to 8 of f of x dx. So what we know in this case is for this integral right here, the integral from 5 to 8 of f of x dx, what we need, given that we have an 8 and a 5, is we need the 5 on the bottom. So if we tried to say that this was equal to this plus this, we would be wrong. But what we can do is we can reverse this. So first of all, we know that the integral from 0 to 5 of f of x dx equals 5. But this is the same thing as saying, if I wanted to reverse this integral, that the integral from 5 to 0 of f of x dx, well, if I negate this, I can negate this, and I can flip my integral. So the negative integral from 5 to 0 of f of x dx is equal to negative 5. Or in this case, we would probably just say negative 5. Because if we negate both sides, then it's actually just the same thing you started with. So if you negate this, we can divide the negative over here, and we get that the integral from 5 to 0 of f of x dx is negative 5. So we've negated something to take into account the flip of the bounds here. And what we need is the integral from 5 to 8. So what we need to do is we need to have the 5 on the bottom and the 8 on the top, and we need the constants that we want to get rid of on opposite sides of our integral signs. Well, now we have that. So if we took the integral from 5 to 0 of f of x dx, and we added that to the integral from 0 to 8 of f of x dx, what we wind up with is the integral from, well, the zeros kind of, you can think of it almost as like canceling out. It's not quite, but you can kind of think of it as that. Combine them, and the 5 takes this spot, and the 8 takes this spot, and you have f of x dx. This is what we're looking for right here. So all we need to do is know what numbers go in here. Well, we just determined this number, right? We said because we needed to negate this, we needed to flip these bounds, we can negate the other side. So this is -5 plus this stays the same. So this is 10 equals the integral from 5 to 8 of f of x dx, which -5 plus 10 is just a +5. So that tells us that the integral from 5 to 8 of f of x dx is +5. So this is a good application of being able to switch your bounds and combine integrals. And we can combine them again because our integrands are the same. All right. Here is a little comparison theorem. This isn't necessarily something that you have to memorize. This is just an interesting note, I want to say. So if your function is positive for all of your a to b, for your entire interval, if your function's positive, then your integral is also going to be positive because your integral is area. So if your function's positive, obviously the area under the function is also going to be positive. That makes sense, right? So from a to b of this function, obviously this is all positive. Now, if you're looking at two functions, f is greater than g on your interval, then obviously your area of f is going to be greater than your area of g. So if this top one is f of x and the bottom one is g of x, obviously the area under this curve is going to be greater than the area under that curve. And then we also have this last one that if lowercase m and capital M are constants, such that lowercase m is less than f is less than capital M on your interval, then we know this fact right here, that m times b minus a is less than or equal to the integral, which is less than or equal to b minus a. All right. And this is something that, again, you probably won't need to know too much, but it's just an interesting thing to note. This, however, is an important theorem. So this says let f be continuous. I should get a highlighter. All right. Let f be continuous on a to b, then the average value of the function, f average, is given by this right here. So the average value is 1 over b minus a times the integral from a to b of f of x dx. So this will be the average value of your function. So it's just the integral from a to b, but then you have to multiply by this 1 over b minus a. So if you're ever asked for average value, this is the formula that you would want to find. All right, so let's go ahead and do an example. Let's find the average value of f of x equals x plus 1 over the interval from 0 to 5. I believe that this is the last one for today. Yep, this is the last one for today. Okay. So, of course, the first step is to graph it from 0 to 5. I've given you the graph because at this point, I think that you guys are pretty good with graphing. You're in Calc 1, you're pretty good. So this is the graph. Once we see this graph, what we recognize is that this is a trapezoid. So what we can do is we can use the area of a trapezoid. This is the area formula that they're giving us. The only reason why we want to use this maybe is because we call this A and B. Base 1 plus base 2 works too. It really just depends on how you see it, what formula you would remember. Any of the formulas are valid though. So it's 1/2 times your height times the sum of your two bases. And we want to find the average value. Well, we know that the integral from a to b of f of x dx is equal to the area of your trapezoid. So first, let's compute this value, and then we could multiply by this value to find your average value. So area of trapezoid equals 1/2. Your height is again going to be your x value. It's going to be your x width. So the distance from 0 to 5 is just 5 times the sum of your bases. So this one is 0 to 1, which is 1, plus this one goes from 0 to 6. So this is 6. So this is 1/2, 5 times 7, which is 35, which gives us 35 over 2. And we'll just leave it as a fraction. So the area of the trapezoid is 35 over 2. So if you were just asked for the integral from 0 to 5 of f of x dx or x plus 1 dx, you'd get 35 over 2. But we're asked for the average value. So f av is equal to 1 over b minus a, which is 5 minus 0, times your integral, which we just determined was this value here when we computed it, which was 35 over 2. Well, 1 over 5 times 35 over 2 is the same exact thing as 7 over 2. So your average value is 7 over 2. All right. That's it for today. So like I said, tomorrow we'll find out how to compute this using antiderivatives. That'll make it slightly easier than having to remember all of your area formulas and do it kind of more brute force by hand. So if you have any questions, as always, let me know. And if not, I will see you for the last two lectures of our course.